Good morning, afternoon, evening, midnight, whenever you're watching this. And if you're watching it at midnight, I mean, come on, get your sleep cycle back to something human. For your own good. Whatever. You're not my kid. You're all my children. No, I'm just kidding. Okay, so magnetism is today's topic. And we're just going to get rolling on it. So this is a picture of a magnet right here. How do I know that's a magnet? Well, you have all these little needles. Those are sewing needles. I know I've shown you this before. For those of you that remember it, just bear with me, all right? And these attach to these red sewing thread, and you see how it pokes through the back of the box there. Someone tied a knot on the other side so it won't come through anymore. And someone took a lot of time measuring these out, so the needles were within the range of the magnetic field without actually touching it. I know this is a box because look, here's the edge of it. Okay, so this shows properties of magnets. Some metals are drawn to them. Not all metals. More of that coming up. Alrighty, so magnetism is. Oh yeah, by the way, I don't have guided notes for this, and I'm not going to make you do any worksheets today. There's 36 slides to go through. I think that's enough for one day. So here we go. The properties and interactions exhibited by magnets. That's magnetism. Properties, things used to describe them. Interactions, how they interact with other things, how they act around other things, like how they act with each other, how they act with certain metals. Exhibited, shown by. There we go. Hope you got it written down. So here's a picture made by taking a piece of paper, putting it over a bar magnet, and sprinkling iron filings on it. Iron filings are made by taking a metal file and scraping it across chunks of iron. The dust that comes off is called iron filings. You capture that dust, you tell it to science teachers, we sprinkle it over pieces of paper that have a magnet underneath them, and we get pictures like this. The N and the S were added on afterwards. Alright, so these loopy lines are very, very common when it comes to magnetic fields. So if you see a picture like that showing you fields of force over and they're loopy like that, it's a magnetic field. Let's see, there's 2 points that the iron filings are kind of pointing towards, the 2 poles of the magnet. More on that coming up. Alrighty then. Let me get my face down there. Magnets are anything that has the property of magnetism. Pause if you need to finish writing that down because I'm about to move on. Okay, here's a picture of 2 horseshoe magnets. So if that's labeled North Pole, that must be the South Pole. And you see some metals are drawn to magnets, but not all metals. That's coming up. So wait, don't write this down, just read and see if you follow. Magnetism is what a magnet has, and a magnet is something that has magnetism. Have I actually told you anything here? No, I have not. This is a very circular logic type reasoning thing. Magnets have magnetism, and magnetism is what magnets have. They're kind of defining each other without telling you anything about them. There's a reason for that, though. It's because magnetism is one of the 4 basic forces of the universe. We've already looked at the strong nuclear force. We've already looked at gravity. Electromagnetism is another one. Electric force and magnetic force are related. More on that in college. Alright? Nobody knows how magnetism is made. We can find it. We can manipulate it. We can control it. But we're not quite sure why it's there or how. Not why. How it's there. We can control it though. We know what it does. You have fun with it. And a lot of things in your life actually depend on it. Things you find important. Just saying. There's magnets in there. Alright, so what we know about it, the force. Magnetic force is the forces magnets exert on each other and on things that can be affected by magnetic fields. While you're writing that down, let me remind you that forces cause accelerations, changes to motion. Forces don't cause motion, they cause motion to change. Yes, I know here in Earth's gravitational field, everything eventually comes to a stop because of gravity combined with friction. And so most things are not moving compared to you. And so a magnet makes things move, as you like to say, but no, it simply accelerates it from a 0 velocity to whatever velocity it has. Whatever velocity the magnet gives it until it hits the magnet. And then Newton's third law comes in. For every action equal opposite reaction, hits the magnet and stops. But whatever. I do have in my class 2 magnets so strong that if you let them go, they'll shatter when they hit each other. They have that much acceleration behind them, that much force. That's why I don't let y'all play with those magnets. All right, got that written down yet? Good. If not, pause. Let's go. A magnetic field is the area around a magnet in which the magnetic force acts. Strongest near the poles, where the lines of magnetic force come together. Weakest the further away you get from the magnet. Strongest at the 2 poles. And that is what you saw. Pause if you need to, because I'm moving on. This is what you saw in this picture again. This is a slice through the magnetic field. Okay, so it's a 3-dimensional thing, and I'll show you a picture of that here in a little bit, but this is a slice through it, so you can see the lines of force in the magnetic field. See out here, they just go outwards. If you follow one of these loops out, they'll eventually come around back to the other side. But the further out you get, the weaker the loops get, the weaker the lines of force get. Okay. Magnetic poles. Places on the magnet where the field strength is the strongest. Every magnet has at least 2. Always 2 poles. Can they be more than 2? Yes, but that's college level crap. Not for you right now. Unless you feel like Googling it, have fun. The thing you need to get in your mind though is there's never less than 2 magnetic poles on a magnet. There's no such thing as a monopole. No. Okay. Pause if you need to. I'm moving forward. Every magnet has a positive pole and a negative pole. Okay. How do I know the pole of a magnet is positive? Because negative charged objects are attracted to it, and positive charged objects are repelled by it. Those two are opposites, so they attract. Remember, opposite charges attract. So if you bring the positive pole of one magnet close to the negative pole of another magnet, they come together and they stick. You've played with magnets before. Please tell me you played with magnets before, or are you playing with some right now while you're watching this? And so you can feel that. Okay? Put the positive pole of one magnet near the positive pole of another magnet, they repel. Yes, you're probably strong enough to make the magnets in your house stick together while you're playing with them. Alright? Even though they're repelling each other, you're strong. Great. But you can feel the force repelling them. You can feel it. Okay. Same thing with 2 negative poles. So opposites attract, likes repel, just like with charges. Same thing happens with poles. Alright. Cool thing. If you let a magnet swing freely, completely freely, the positive pole will always end up pointing north, which in my house is that way. That's why we call it the north pole of the magnet. I hate calling it the north pole because it gets confusing here in a minute. I'd rather call it the north pointing pole because it points north. But they don't. They call it the north pole of the magnet. So the negative pole is the south pole because the positive pole is the north pole. The positive pole will point north if you let it swing. So it's the positive. Is a negative. The north pointing pole, the south pole. The negative pole is the south pointing pole. Think about it. If the north one's pointing north, the south one's pointing south. They're opposite ends of the magnet. Okay. Why is this confusing? Well, I'll tell you in a minute. So remember, if there's a little N on it, it's the positive pole. If there's a little S on it, it's the negative pole. Got it? Remember that. Okay, the direction of a magnetic field is by convention. That means by agreement with everybody who works on magnets. Defined as the direction a positive charge would go if placed in the field. Remember, forces are directional. Magnetic fields are fields of force. What's the direction of the field of force? Well, it depends on your charge, really. A positive charge will go towards the negative south pole. The negative charge will go the other way. Got this written down yet? No? If not, pause, finish writing, and then go here. The north pole of the magnet is the positive pole. The south pole is the negative pole. A positive charge placed in the magnetic field would move towards the south pole. Pause if you need to, then come back. So, when you draw a magnetic field, and please add this as a little drawing in your notes, don't make it too big, just a tiny little drawing will do. The arrows on the lines of force always point towards the South Pole. Understand that's just what a positively charged thing would do, like a proton or a piece of dust that's positive would go that way. A negatively charged object like an electron or a piece of dust that's negatively charged would go the other way from the arrows. But the arrows always show you which way is positive. So if I had this drawing without the south and the north in it, just the arrows, you could fill in the south and the north for me. The arrows point towards the south negative pole, the south pointing pole. Okay. Here's the confusing part. The Earth also has a magnetic field. That magnetic field affects magnets. That's how a compass works. Remember, if you've ever never seen a compass, it's a needle that's free to swing about if you hold it perfectly horizontally. If you hold it up and down, it doesn't work. You've got to hold it perfectly horizontally, and that needle will swing and eventually settle, pointing in one direction. The red end, I believe, of the magnet is always the one that points north. Isn't the red one? Whatever. One of those ends points north. So the Earth has a magnetic field. Here's a drawing, a cutaway version of the magnetic field. And you see North America there, South America there. So the direction north is up here, the direction south is down here. And the arrows are pointing towards, they're supposed to point towards the south magnetic pole, the negative pole, aren't they? But they're pointing in the direction we call north. Alright, so this is the shape of a magnetic field. If you look back here in 3 dimensions, it's kind of like a donut. Just cut it in half here so you can see the lines of force inside of it. This would be the Earth's magnetic field shape if there was no sun, but we have the sun, and the sun is putting out this stream of charged particles called the solar wind that has a really big effect on the Earth's magnetic field. It reshapes it to that. So not to scale. If we were that close to the sun, we'd be fried, crispy critters. We'd have no oceans, we'd have no air, it'd all be fried away by the sun. But not important right now. So this white stuff is the solar winds, the charged particles coming off the sun. And you see the Earth's magnetic field blocks it. After being squished a bit, it does block it. Some of those charged particles travel along the poles of the magnetic field to the Earth's atmosphere. Not many of them, but some. So when those actually hit the Earth's atmosphere, you get the aurora borealis and the aurora australis, the northern and the southern lights up in the sky. You've never seen them? I'm sorry. Google that stuff. Northern lights. Okay. Think about this. A magnet's positive north pole is defined as the pole that will point to geographic north, the north-seeking or north-pointing pole. So the north pole of a magnet is called the north pole of a magnet because it points north if you let the magnet swing freely. Need to wet my whistle here. Okay. So opposite poles attract. So if a magnet's positive north pole points north, and the Earth's negative south magnetic pole must be at the north geographic pole. You get it? Let me just show you a picture. Okay, first off, there's no such thing as a gigantic bar magnet inside the Earth. It's not what's happening here. It's just to show you the south magnetic pole of the Earth is up here at the north geographical pole. The direction we call north has the negative pole. That's why the positive end of the magnet points north, because the Earth's negative magnetic pole is up there. So the north pole of the compass points to the south pole of the Earth's magnetic field. See, this is why I hate calling them north poles and south poles of a magnet. I'd rather call it the positive and negative pole. Whatever. Oh, and if you want to add to the confusion, every few 100,000 years, this thing flips. And the negative pole will be down there, and the positive pole will be up there. Hasn't happened in recorded human history, but recorded human history only goes back at most, 10,000 years, not even. This flip-flop is recorded in the rocks, especially at the spreading centers of the Earth's crust out in the mid-Atlantic ridge. You learned about it in Earth science. Whether you were paying attention or not, I don't know, but you were taught it. Okay. Now, the next little segment. If you want to take a breather, pause, go pee, get something to drink, snack, whatever, come back. That's fine. It's your house. It's your life. I'm going to move on. What is in a magnet? Well, all magnets have iron, nickel, and or cobalt in them. If you look at the periodic table of the elements, those three elements are right near each other. They touch each other on the periodic table. These three elements are called the iron triad, and their atoms have tiny little magnetic fields around them. How? I don't know. Why? I can't answer that either. But they do. They consistently do. And now that we know that, we can use that to our advantage. Don't know how it got there, but it's there. Alright? All items made from these elements will be affected by magnetic fields. If you have a little magnet with you right now, you could pause, go around the house, and see what it sticks to. Don't take too long. I only want an hour of your time today. But you can play with the magnets all you want. Whatever. Just don't try on the cat. It's not going to stick to the cat or the dog. Alright? Jesus. If you have a relative with a steel plate in their head, please don't do that. That's just not funny. That's just rude. Anyways, go play. Come back. You back? Okay. But not all items made from these elements are necessarily automatically magnets. They'll all stick to a magnet, or a magnet will stick to them, but they're not all actually magnets necessarily. Okay, so how do I take a chunk of steel that's not a magnet and turn it into a magnet? Here we go. In atoms made from these elements, each atom has its own little magnetic field. I already told you that. Large groups of these atoms, large means a few thousand atoms, which, okay, is still too small for you to see, but whatever. They line up with each other and form magnetic domains. So what's a magnetic domain? Large groups of atoms where all little north poles point the same way. What kinds of atoms? Iron, nickel, or cobalt. Those are the only three kinds of atoms that have magnetic fields around them. Alright. If all these little domains have their own little directions that they're pointing, you do not have a magnet. They cancel each other out. The little magnetic fields overlap and cancel out. If all the domains line up, you get a magnet. Pause, write that down, then come back. Here we go. So this picture here, unmagnetized iron. This picture here, magnetized. These little tiny little magnets represent domains within the chunk of iron. Alright? And they're all pointing in different directions, so they cancel each other out. If you manage to get them all to line up, how do you do that? You make the atoms twist in place. How do you do that? Put them in a stronger magnetic field. Take a chunk of steel, put it in a strong magnetic field, and leave it there long enough. The stronger the field, the less time you need. All the little domains will be tugged into alignment. The longer you leave it in there, the more domains are tugged into alignment, and the stronger the magnet. If you don't like this picture, there's this picture here. Here's a bar of steel. The arrows show you which way the little domains are going within those areas. So here's a domain, here's a domain, here's a domain. This is not magnetized. If you get them all point in the same direction, all the fields overlap and multiply with each other, and you get a magnetic field around it. You get a magnet. Cool. Cool. Okay. The more domains line up, the stronger the magnet, but remember, all these magnets that we're dealing with exist on Earth, inside the Earth's magnetic field. Not super duper strong at any one point, but it's a constant tugging on the atoms inside your magnet. So eventually, domains get tugged out of alignment, weakening the magnet until no longer there is a magnetic field. All magnets eventually die. No, that's morbid. All magnets eventually demagnetize. That's a little more accurate. They weren't alive to begin with, they're just magnets. Permanent magnets, we call them permanent because they keep the strength for a long time, thousands of years. Okay, so it's not permanent. It doesn't last forever, but it lasts longer than you or I will. You're not immortal. So it'll last longer than you. Temporary magnets are made by placing magnetic material near a permanent magnet. Try this. Take your magnet, put a paperclip near it, or on it, And then take that paper clip and touch other paper clips with it. Pick it up. Or if you don't have paper clips, maybe try some nails. Put one nail on the magnet, and then try to pick up other nails with that nail while it's still on the magnet. It works. Temporary magnet. You take the nail or the paper clip off the magnet. Can't do it anymore. Play with that if you want to. I'm moving on. How to demagnetize a permanent magnet. You know these things. Other than waiting thousands of years for it to eventually demagnetize itself. Oop, never mind. She's fine. You could heat it up. You could beat it up. How does that work? You're shaking the atoms. You can shake them out of alignment eventually. The more you heat it and the more you beat it, the more the little domains come out of alignment, and the less magnetic force you have. Eventually you can get them all out of alignment and it's no longer a magnet. Can you isolate one pole by breaking a magnet in two? Snap. I've got one north pole and one south pole. No, you can't do that. Can you figure out how that works? No? Well, we're not in class, so I'm not going to wait for someone to say it. I'm going to say it. So even though you've got a broken magnet, each piece has the domain still lined up. So each piece has a north and a south pole. So if you look here, you see the lines of magnetic force going from the north to a south pole, the loops and everything. You break it in half. Each one has a north and a south pole, a north and a south pole. And if you look here, they're interacting with each other in such a way that they attract each other. So if the lines of force go from one magnet to another, they're attracting each other. If I flip this magnet over, they repel each other. I don't have a picture of that. I'm sorry. And another picture, cartoony picture showing you, no matter how many times you break it, each piece is a north and a south pole. You cannot get a single pole by itself. Okay, it only took 22 minutes. I'm not doing this one today. I'm going to do this one next time, which will be Monday. Alright, so let me exit. Let's get rid of that. There we go. And y'all have yourselves a lovely day. Enjoy.